For more than 60 years, Bruker has created innovative analytical instruments to support the scientific community as well as users in industry. Our analytical solutions stand for cutting-edge technology and highest performance. While we are providing top technology for scientists worldwide, over the past decades, we have more and more focused on making the latest analytical methods also accessible to a broader group of users. At the forefront of this endeavor for accessibility are our benchtop instruments. Although they come with a smaller form factor than our landmark full-size systems, they share with them the same analytical instrument DNA, including the focus on data quality, robust hardware design, and reliable results. Today, we are happy to introduce a new member of our benchtop solution family, the D6 PHASER. The D6 PHASER is the base of a new world of X-ray diffraction solutions with compact size and unparalleled flexibility.
When it was released in 2009, the D2 PHASER X-ray diffractometer strongly resonated with the user community. The all-in-one benchtop system with its innovative, highly accurate goniometer and the integration of components from our floor-standing instruments convinced with exceptional data quality in a small package. The combination of a small measurement radius and full-size one-dimensional detector enabled a high sample throughput. That proved the D2 phaser running at just 300 watts competes with floor-standing instruments for standard X-ray powder diffraction in many market segments. You cannot rest on your success. Customers accept further innovations. Consequently, over the last 14 years, we released updated version with the option of a sample changer in our most advanced linear detector, the LYNX XCT. Today, the D2 phaser is the world's best benchtop X-ray diffractometer. Nevertheless, a few years ago, we started thinking about the next generation of the D2 phaser. The original idea was to keep the things that users love. Keep the benchtop form factor, but go for more power and add more sample stages. Then we asked ourselves whether there were other unique technologies in our D8 XRD family that could be transferred to the D2 phaser successor. Logical steps were to integrate a motorized slits and a motorized air scatter screen for a full implementation of the dynamic beam optimization. A new stage interface was designed, enabling the user to swap sample stages without realignment. Naturally, sample stages were adapted, which enabled further X-ray diffraction application, capillary transmission, grazing incidence diffraction, X-ray reflectometry, the residual stress and texture analysis, and last but not least, non-ambient investigations. Now it's time to introduce the new D6 phaser to the user community. The D6 phaser benchtop X-ray diffraction offers unrevealed and easy-to-use analysis possibilities. I'm convinced that the new instrument will define a new class of X-ray diffractometers. And the reason is that the new D6 phaser bridges the functional gap between the traditional benchtop and the floor-standing instruments by expanding the analytical potential beyond powder.
The D6 phaser is the most powerful and versatile benchtop X-ray diffractometer on the market. With an available 1200 watt generator, the D6 phaser challenges the performance of traditional floor-standing systems. This power, combined with the small goniometer radius, increases the amount of signal to over 4 times that of our previous benchtop model, the D2 phaser. The user benefits from approximately 2 times lower detection and quantification limits, or faster measurement and sample turnaround times. The X-ray tube is cooled by an internal cooling circuit, eliminating the need for an external chiller. This reduces infrastructure requirements to a minimum and keeps the ecologic footprint, but also the costs of ownership low. Of course, users who already have a cooling circuit available in their laboratory can optionally continue to use this existing infrastructure. Another important aspect of signal throughput is the detector. The D6 phaser can be configured with all 3 members of our LYNX detector family, including the SSD162, LYNX i2, and the LYNX XCT. The XCT detector features an energy discriminator capable of separating K-beta from K-alpha radiation without the need for traditional metal filters. This eliminates artifacts while increasing the usable signal. All 3 detectors can be operated in 0D, 1D, and 2-dimensional modes. Unmatched versatility combined with highest data quality are signature features of the D6 phaser. This starts with the primary beam optics. The advanced primary optics allows measurements in both divergent and parallel beam configurations. Combined with the motorized anti-scatter shield and variable detector opening, the D6 phaser is capable of dynamic beam optimized measurements. In this mode, the user simply enters the sample size and the system handles the necessary adjustments. This not only ensures excellent data quality, but also minimizes operator training, leaving the optimal choice to the instrument. Using special primary and secondary beam optics, measurements beyond Bragg-Brentano geometry can be performed in capillary and grazing incidence geometry, including X-ray reflectometry. To ensure that the D6 can handle a wide variety of samples and experiments, We not only designed multiple stages, but also an entirely new interface for mechanical and electrical connectivity. Not only does this make it a breeze for users to add stages that are currently available and to swap those stages on their own, it also makes it much easier for us at Bruker to develop further stages in the future. Of course, for standard powder diffraction, the single position rotation stage and the rotation sample changer are available, with the new changer supporting up to 12 samples. We also have a new stage capable of standard reflectance, but also flat sample transmittance measurements. Another innovation is the completely new capillary sample concept. The capillaries are mounted on fixed or fine adjustable bases, which are then magnetically attached to the spinner in the instrument. If your requirements go beyond the current temperature conditions in the laboratory, the D6 PHASER supports unparalleled BTS 150 and 500 stages. This allows users to measure samples from -10 to 150 degrees centigrade and from room temperature to 500 degrees. One of the setups I'm most excited about is the universal stage. This stage combines high-precision sample tilt and height modules to facilitate materials research measurements, such as residual stress, X-ray reflectometry, and grazing incidence diffraction. This stage acts as a platform for additional accessories, including a vacuum finger for small wafer pieces and an indexed phi module to enable texture measurements. Obviously, the phi rotation module also supports routine powder diffraction in Bragg-Brentano reflection geometry, which makes this setup truly universal. To bring it all together, we put a lot of effort into the user's experience. When you walk up to the D6, there is a touch screen that displays the current status of the instrument. Unlocking the door, turning on the generator, and starting a measurement template can all be done right from the operation touchscreen. For more detailed investigations, we use the familiar Diffraction suite to control the D6 PHASER, evaluate the measurements, and present the results in the same way as the larger floor-standing machines. The platform design of the D6 PHASER allows us to expand the benchtop concept with more tools and accessories for many years to come, continually pushing benchtop XRD beyond standard powder diffraction.
Once the system requirements have been established, it's our job to bring the product to life. In case of the D6 PHASER, this meant many technical and logistical challenges. Bruker is a global company. Research and development for the D6 PHASER was carried out in Karlsruhe, Germany, while prototyping and production is located in our Center of Manufacturing Excellence, Penang, Malaysia. We have a strong relationship with our colleagues in Penang, as they have been building the D2 PHASER and several other benchtop instruments for many years. The D6 PHASER user requirements presented many engineering and physical challenges. A few of those that stick out to me were the internal cooling system for the 1.2 kilowatt generator and the new motion control system. The process to create X-rays creates a large amount of heat. In the floor-standing instruments, this is typically handled with a large external cooler. For the D6 PHASER, we wanted to keep the footprint of the instrument to an absolute minimum, which meant designing an internal cooling system capable of handling 1.2 kilowatts of power. After testing many different prototypes, we found just the right balance of fans and radiators to efficiently dispatch the heat from the tube while maintaining quiet system operation. To ensure the air entering the system is clean, we have included large and easy to maintain filters. Traditionally, our systems have used a centralized motor control concept. With the D6 PHASER, we decided to use a decentralized system. Each component contains its necessary motors and drivers. This makes it extremely simple for the user to add additional components to their instrument, as the connections are located right in the experimental chamber. For example, the connections for the stage and mask are conveniently located near the mounting interfaces. An important aspect of developing a commercial analytical instrument is to ensure that we meet the latest regulations for mechanical, electrical, and X-ray safety. It starts with a bulletproof safety concept where two circuits ensure that the system is safe. This includes door locks, many sensors, and a dedicated safety board to check that the instrument is in a safe state, and of course a factory test of the entire radiation enclosure to ensure it is radiation tight. Each motorized drive is checked and assigned a class, which determines if it can move with the door open or closed. The testing does not stop here. We then ensured that parts of the electronics enclosure meet IP54 by throwing dust and spraying water into the fans. Do not try this at your own lab, but be assured the D6 made it through this test with flying colors. The development of the D6 phaser does not stop with this release. We already have more components lined up in the development lab for future releases. This is one of the aspects of the D6 I'm really excited about. As new technologies are discovered, the backbone systems in the D6 means that we can create new attachments to extend the D6 phaser.
To simplify making capillary measurements, we approach the design of the capillary solution for D6 phaser by thinking about the whole process, from aligning the capillary through to collecting the data. This drew on my experience supporting user experiments on synchrotron beam lines, where rapid and reliable alignment of many capillaries is crucial. The result is an entire ecosystem of accessories with capillary holders and alignment tools tailored for the variety of capillary shapes and sizes that are used in the lab. Capillaries are pre-aligned using the capillary alignment tool, CAT. The user first selects a capillary holder, which has the right size for the capillary to be mounted, and two CAT inserts with holes which are also the appropriate size for their capillary. For drawn glass capillaries, inserts can be chosen which are smaller to allow for the conical shape of the capillary. After mounting the inserts in the CAT, the user mounts the capillary holder in the upper insert. The capillary is then threaded through the 4 concentric holes and glued in place. For capillaries with diameters of 0.5 mm or larger, no further alignment is needed. The D6 phaser creates a narrow parallel beam using an advanced primary optic. This optic, the guard slit holder, minimizes air scatter from the primary beam and includes an adjustable beam stop. It is complemented on the detector side using the telescopic slit shaft, which places a slit near to the capillary. This ensures the detector only sees X-rays coming from the sample and thus keeps background scatter to a minimum. All components are compatible with all tube types. The capillary stage is compact in design but has a versatile feature set. The first and foremost is designed to spin the sample in the center of the goniometer. Goniometer heads for mounting capillaries are attached magnetically to the stage and centered using a cone-shaped interface like those found in precision CNC tooling. There are two forms of goniometer head, a fixed and adjustable type. With the fixed type, the pre-aligned capillaries can be mounted and measured straight away on the stage. The adjustable type has tilt and translation axes which allow for fine adjustment of the sample, which is only necessary with capillaries with diameters smaller than 0.5 mm. A USB microscope is available to precisely align the capillary and minimize precession during spinning. For the instrument verification procedure, we designed a reflection sample holder which is mounted on the fixed head. It comes with a pre-mounted corundum sample and allows the user to verify the system is ready for measurements. We also created a reflection holder which holds a small amount of powder in the capillary stage mount. The capillary solution for D6 phaser goes beyond a rotating stage and makes the process of aligning capillaries trivial, thanks to the collection of accessories we've developed.
Our X-ray diffraction software solutions revolve around a very simple concept: plan, measure, analyze. Users are guided through analytical methods in an intuitive, non-obtrusive way on our extensive knowledge of XRD analytical methods. Planning starts with configuring appropriate component setup for your measurements. For the D6 phaser, this setup occurs in DaVinci, a graphical representation of the instrument where the user can choose the components to use. Our software gives clear instructions on the steps needed to configure the instrument. Wizard is then used to plan method files for measurements. Users are guided step by step via interactive templates to define measurements ranging from routine powder diffraction to more advanced features such as measurements with variable step size and variable counting time, non-ambient temperature profiles, texture, stress, grazing incidence diffraction, and X-ray reflectometry. Commander offers several ways to execute measurements on the D6 phaser. The immediate measurement interface gives direct control of instrument, including generator power, configured access, and scan conditions. The interface automatically reconfigures based on the components that have been chosen in DaVinci. Once a measurement begins, live scan data can be seen on the interactive chart. The second way that measurements can be lodged is through the job interface. This is where the method files from Wizard are used. If a sample change is configured, specific methods can be set for each position. In addition, a push-button interface is available where method files can be executed with a single click of the mouse or a touch on the D6 touchscreen. Measurements are stored in the result database and can also be saved as a file to a specific location. Automated analysis routines can be lodged using our comprehensive scripting platform. The result of these analyses can also be stored directly in the results database. Analysis is delegated to our well-known suite of applications. They provide access to simple, easy-to-use methods, as well as the ability to dig in deep into your data to reveal the properties of interest. Access to Diffract Suite can be controlled using the user database, ensuring that the right people have access to the right features. Speaking of databases and user control, Diffract Suite and many of the analysis applications are available as GXP-compatible solutions. Of course, this includes compliance with the 22 CFR Part 11 protocol of regulated industries. The implementation of our plan, measure, analyze concept in Diffract Suite gives users of any experience level the ability to take full advantage of the multitude of analytical techniques available with the D6 phaser, allowing them to push their work beyond standard powder diffraction.
The reliability of measurement results is a basic requirement of any data analysis. Traditionally, this required following a special alignment workflow, including processing of the data and interpretation of results against standards. In many areas where X-ray diffraction is used, this validation and verification procedure is essential. The D6 phaser features a wide range of stages which can easily be switched by the user. These stages incorporate a high-precision mounting interface, but it is important to verify that the system is ready using a standard sample. On startup, the verification status of the instrument is not known. A yellow questioning face appears. On a touchscreen, you will find two push-button methods available for initiating the verification process. One button will perform the verification test based on the measurement of a standard corundum sample. Depending on the features available on the stage and the tube anode material, this verification may include the peak position, relative intensity, and full width at half maximum of 4 peaks across the measurement range. This will result in a generation of a report showing the calculated value and easy to identify icon with a green smiley indicating the system is ready to use, or red frown if the system needs new reference values. If the red frown is shown, simply press the referencing and verification button. In this case, the system will run through a referencing of the goniometer axis. Once this is complete, the system will confirm it is now within specification, resulting in a green smiley. The whole verification procedures follows our general acceptance protocol. Diffraction peaks of the standard corundum sample will be within 0.01 degrees 2 theta, relative intensity within 10%, and full width half maximum less than the expected values. These methods are valuable not only for checking the system's suitability after stage exchange, but also if new stages are being added to a current existing instrument. Our easy-to-use push-button verification standardizes the IQ-OQ process. That means that the installation and functional qualification of the instrument, and at the same time gives the user a built-in tool at hand to regularly execute routine performance qualification to ensure best possible data and comply with the GMP process. One of the hallmark features of the D6 phaser is the ability to adapt the system to a multitude of measurement types beyond basic powder diffraction. Our hope is that these tools give users a high level of confidence in changing components so that the instrument can be used to its fullest extent.
Like its predecessor, the D2 phaser, the D6 phaser is a great instrument for powder X-ray diffraction experiments. The phaser goniometer allows the collection of high-quality data with a small measurement radius. Combining the small radius with a new 1.2 kilowatt generator and LynxEye XCT results in the signal levels revealing the most powerful floor-standing equipments. The Bruker accuracy guarantee ensures that all peaks on the standard corundum sample included with the instrument will be within 0.01 degrees of their anticipated peak locations, meaning that not only the individual components, but the system as a whole is capable of extremely accurate measurements. The standard stage allows the collection of both reflection and flat plate transmission data. If the sample contains larger grains or the potential for preferred orientation, a sample spinner attachment can easily be exchanged. This allows reflection measurement using standard 51 mm holders. If you have the need for measuring multiple samples, the 12-position changer is a great option. Similar to their other stages, it attaches using the high-precision stage mounting mechanism. These stages are all compatible with a motorized air scatter shield. With a mass, all you need to do is enter the size of the sample and the screen position is automatically optimized based on the angle of incidence. To push your measurement even further, you can upgrade to the advanced slit assembly. The motorized slit unlocks the full potential of the dynamic beam optimization by setting the ideal beam size based on the angle of the goniometer. At low angles, the slit closes down, and at high, it opens up to maintain coverage of the entire sample surface while maximizing X-ray flux. The mask and the detector opening are also kept in perfect synchronization to attain ideal powder diffraction data automatically. DBO is exceptionally good at collecting low-angle data where the beam shape needs to be carefully controlled to prevent high background. Once you have collected the data, Diffract.eva reads the BRML file, automatically compensating for instrumental conditions, such as the variable detector opening used during DBO measurements. For users working in a GXP environment, the D6 phaser and EVA are available as a compliant solution. The new capillary stage allows you to take transmission measurements to the next level. Once the stage is mounted, samples are attached using a magnetic interface. For standard capillary work, you can use the gluing apparatus to mount the sample. For smaller capillaries, a fine tilt head is available. We even developed an attachment for measuring small reflections powder samples without having to remove the capillary stage. To properly condition the incident and diffracted beam, a set of attachments have been developed which include a beam stop, scatter reduction slit. A typical capillary measurement is the collection of high-quality data for crystal structure determination. In this case, diffractor topaz is used to index and refine the unit cell. Sometimes investigations go beyond standard laboratory conditions. This is where non-ambient stages come in. The D6 phaser has been designed to seamlessly integrate both the BTS 150 and 500 stages from Anton Paar. Not only does that integration include the ability to mount the stage, but also the ability to plan complex temperature ramps and dwells in the wizard. Another unique powder measurement to Bruker solution is called BRAC2D. In BRAC2D, the full divergent beam geometry is used in combination with a 1D detector to collect a two-dimensional diffraction scan. This allows quick identification of sample preparation issues, such as preferred orientation and large crystallite size, which may affect the relative intensities of peaks in the 1D data. The power and versatility of the D6 phaser allows powder X-ray diffraction to go beyond basic scan.
One of the most unique aspects of the D6 phaser is its ability to bring measurement beyond powder diffraction into a benchtop system. The key to unlocking these measurements is the universal stage. This stage incorporates high-precision tilt and sample height drives into a simple user-exchangeable module. This allows decoupling of the source and detector angles relative to the sample and placement of the sample surface into the exact center of the goniometer motion. Thin films, sometimes referred to as coatings, allow engineers to change the properties of the surface of the material. These coatings can be used to modify the surface finish, add protection, or bring electrical and magnetic properties to the component. Oftentimes, measurements are carried out with a low or grazing angle of incidence to reduce the penetration of X-ray beam into the underlying substrate. Grazing incidence diffraction, also called GID, is most commonly used for phase identification, but can also be used for depth-controlled residual stress analysis using the multi-HKL stress method. Another technique carried out at very low angle is X-ray reflectometry. In an XRD experiment, the intensity of the specular reflection from the sample is measured as function of angle of incidence. The resulting pattern can be used to determine the thickness, roughness, and density of thin layers on the sample surface. Both of these techniques require the use of a thin parallel X-ray beam. In the D6 phaser, this is accomplished using the advanced primary optic. To further refine the beam condition, a secondary optic is placed in front of the detector. In the case of GID, a parallel equatorial solar, and for XRD, an extended slit attachment. Analysis for GID scans typically involve phase identification, which is performed in diffract.eva, while analysis of reflectometry data is completed in diffract.xrd. Another advanced X-ray measurement that is enabled with a universal stage is residual stress analysis. Before a material deforms plastically, it will elastically absorb the force. A common example is cold working metal. The effect occurs through expansion or contraction of the atomic structure of the sample. X-ray diffraction is the ideal method for measuring the stress that has been stored, as we can directly determine the deformation of the unit cell. For this measurement, a high-angle peak is chosen, ideally above 100 degrees to theta. Measurements are carried out as the sample is tilted from the horizontal position. This tilt is called the psi angle. When the strain of a unit cell is plotted versus sin squared psi, the residual stress can be determined. The residual stress method can even be expanded to measure the entire biaxial stress tensor, if this measurement is repeated at different in-plane rotation of the sample. To accomplish this, an indexed phi module can be added to the universal stage. The indexed phi module allows precise rotation of the sample. Planning of the measurement is completed in Wizard, which steps you through setting up the entire measurement. Once the measurement is complete, diffract.leptos is used for analysis. In addition to allowing biaxial stress measurements, the index phi attachment gives access to texture measurements. Texture is the measurement of the orientation of the crystallites that make up a sample. For some applications, a specific texture is required to maximize properties. The 2 theta for a peak of interest is selected, and a series of phi scans at different sample tips are collected. These scans are plotted in a polar coordinate system, resulting in a graph called the pole figure. The measurement is repeated for several diffraction peaks. The pole figures are then loaded into diffract.texture, where the overall orientation distribution for the sample is calculated. Advanced techniques like grazing incidence diffraction, X-ray reflectometry, residual stress, or texture analysis were only possible in floor standing system equipment in the past. The D6 phaser with a universal stage brings the measurement in the benchtop system domain.
Thank you for taking the time to learn about our new D6 phaser. We are very excited to share it with the scientific and industrial community, and we look forward to talking with you about how the D6 phaser can help you push your work far beyond powder diffraction applications.